Hi everyone, I hope that you're doing well. In this lecture, I want to introduce you to the binomial theorem. Here's a fun bit of motivation. Guess which pioneering sociologist is responsible for this excerpt? The labor time needed to reproduce many scientific findings has no relation at all to the labor time required for its original production. For example, a school child can learn the binomial theorem in an hour. So that was a passing comment made by none other than Karl Marx. By the way, these are not his real teeth. This is just a funny image that was shared in a group I'm in on the internet many years ago. Okay, so takeaway, the binomial theorem, and we're really not going to learn the binomial theorem, we'll learn the binomial distribution, which is closely related, is quite easy. So, what does it tell us? Well, here we've been talking about dummy variables in the last few lectures, and we've been describing the distribution of those variables for individuals. So, an individual binary outcome, also known as a dummy or a Bernoulli, comes from a population distribution that's got a mean of little p. And that's the probability that any individual will be a 1. And so it also has implicitly another parameter q, which is 1 minus p, but we don't have to get into that. So these distributions are really simple. To picture it, imagine a bar graph with only two values. We've seen those things before. But we might be interested to know things about the distribution of, say, group level outcomes, such as sums of binary outcomes. And so a sum of a binary outcome for a sample of size n actually comes from a distribution which has mean np and a shape very close to the normal for surprisingly small n's. So we know basically how this individual outcome is actually distributed across entire samples. So we know how the sums, which are very closely related to the means, by the way, are distributed across entire samples, which is a really cool fact that we'll use. This is known as a sampling distribution, even though it's not often referred to this way. The binomial distribution is a sampling distribution, which is a key concept for our course, and we don't ever actually have to observe it. So we don't need to take a bunch of different samples and then say, okay, let's try to plot some kind of histogram here. We can derive its probability mass function easily. It happens to be this, which looks a little intimidating. I'm not going to get into the details right now. You can just kind of absorb this, and we'll explain the details in quite a lot of detail in a moment. But we can simulate that probability mass function to convince ourselves by taking many samples. I show computer simulations, and today, probably this will actually have to wait until Wednesday. We'll do one in real life with coins. So if we knew little p, or the probability of a success on a single realization of the dummy variable, we could figure out the binomial probability big P of a sample of size n from that distribution, which has k successes, or k or more, or k or less, much like we've sometimes looked at normal distributions and we are interested in the area above a certain point or below a certain point. We actually can figure out exact probabilities here because this is a mass function, not a density function, but you'll see that the binomial distribution starts looking like a density curve soon enough, and our purpose will usually be to take the probability of k or more or k or fewer successes. That should be fewer, not less, by the way. In some specific applications, this is useful, but it is often unrealistic. So here's an example where it would work. If we flip a fair coin, or we roll a 5 or not on a fair die, these are dummy or binary outcomes. Note that the die, by the way, has 6 outcomes, but 5 or not is a binary outcome. And these have population probabilities that are knowable. It's just simple physics. So it's 0.5 for a well-crafted coin and 1/6, or about 17%, for a well-crafted die. We don't need any special theory to know that these are true. We can just use our intuition for what probability consists in. And remember that that's the share of events satisfying some outcome in the long run out of all the total possible events. So note that in this case, by the way, these populations, the total number of coin flips, the total number of die throws, are infinite. And this is actually a more natural way to think about populations in many cases, as I've alluded to before. So I want you to kind of start thinking about populations as unknown parameters, or sometimes known parameters, but in any case, like almost like settings or hard facts. You can almost think about it as like if you imagine some kind of deity is having a kind of machine or a program that sets certain physical facts for human beings, and when the deity could turn the knob this way, and maybe the deity could make knob have a 0.6 probability of flipping a fair coin and getting a heads. So we typically don't know those things. That's one reason I'm using that kind of theistic language, but sometimes we do. But the key thing you want to think about is what makes something a parameter. When we say parameter, literally the word means unknown measurement. Sometimes we do say parameter, though, to refer to the rare cases where we do know it, and then the connecting feature is that these are like fixed properties of the world, at least in one way of thinking about things. So in practice, however, we typically don't know P. Because we typically don't know parameters, that's literally why they're called parameters, meaning something that is defectively or unusually measured, literally, but in practice means actually just not measured. But we do know K, so we get a sampling observed K successes, or we take the proportion. For example, we typically don't actually know the probability that someone is employed or not in the US, which is a binary individual outcome. Even if we take a census that's going to miss people and it'll be dated by the time it's complete. But key point here, from this information, we can figure out the probability that some big X, which represents a sample outcome, is greater than or equal to K given some P naught for a simple random sample. P naught here represents a hypothetical value of P, or in other words, the probability of success for a single person. And we supply this hypothetical value. It's a hypothesis made by the researcher. So for example, I might supply the hypothesis that there is 5% unemployment, meaning that there is a 5% probability that a randomly selected individual will be unemployed. If the probability of the sample like this, denoted big P here, is small, we reject the null hypothesis that little p is equal to P naught. And I really need you to understand that big P and little p are totally different things. Little p is the probability of a success on an outcome for some individual. We typically don't observe it. Big P is a probability of a sample that has this number of successes. And these just refer to entirely different things. And this big P requires basically either some kind of hypothetical population parameter or a known population parameter. And the parameter is little p. So this big P here requires us to supply, like literally in the calculation of it, as we'll see, it requires us to supply some value for little p. A lot of times people denote little p with pi, the Greek letter pi, and I'm very tempted to do that because I think it can avoid confusion. The problem is that little p is very, ensconced in the discipline. And this leads to an interesting point, which a lot of people say that Greek letters are intimidating and elitist or something like that. But I found that when people try to use Roman letters for everything, it gets really confusing. Capital and lowercase p are the same shape. They're just, kind of shifted up and down on the page. So I've tried to distinguish them here by writing big P as just bold, little p. Generically, even though it's bolded here, it's just bolded for emphasis, but generically it won't be bolded. But that said, these two things are easily confused. I've also used theta in the past for little p. Again, people tended to find it confusing that I use different notation than the book, but I found that people also will confuse big P and little p. So you just have to keep them separate. One is a probability for an individual, and it's the probability of success on that outcome, that's little p. The other is the probability of a sample of this size. It's always implicitly a conditional probability. It relies on some value of little p, and that's the big blackboard bold P. Okay, so we need to start actually in kind of a funny place. We're going to start really simply. We want to learn what factorial notation means. So when someone writes n factorial, that's what this is here, by the way, this exclamation mark, it means do the following. N times n minus 1 down to 3, 2, and 1. So let's practice. Try to do 5 factorial. I'll give you a second. You should pause the video here. And then coming back together, there's an easy way to calculate this in your head. 5 and 4 is 20, 3 and 2 is 6, so our answer is 120. The formal definition of n factorial is given below for reference. You may see this capital P here, or this is actually pi, sorry, not P, although the Greeks may have pronounced it P, I don't know. But anyways, this is the product of a sequence operator, much like capital sigma is the addition of a sequence. So for instance, this notation here tells us to multiply every observed value of x by, basically multiply every observed value of x. I don't need to say it any more complicatedly than that. So formally speaking, n factorial can be written very simply as multiply together every number from 1 to n. So now we need to talk about permutations. So we're now going to think about a kind of a different puzzle. 4 ways to consider the selection of k items from a set of n. We'll start with permutations, which are a case where order matters and repeats are allowed. So, well, and I should be a little bit more precise. So sometimes people restrict permutations to mean only the situation where repeats are not allowed, but there's actually not harmony in the discipline on this. So the point that we're going to focus on more in reality is cases where order matters or doesn't matter and repeats are not allowed. But let's start with repeats allowed. So this is pretty easy to conceptualize. So what's a case where you could repeat an outcome? Maybe it's easiest to start by thinking about a situation where you could not repeat an outcome. So imagine having a bag full of billiard balls. You're going to go play pool, and you pull the 8 ball, or you pull the cue ball or the 1 ball. Once you pull those things, which you can think about as an experiment or a trial, then you can't do it again. So that's an unrepeatable outcome. Conversely, if you flip a coin and get a head, or you roll a die and you get a 5, then you can get that same outcome again. So that means you can reuse or replace them. So we're going to focus here on this cell. By the way, this cowboy here is just because this formula is a little scary looking and we don't need it. Order matters, doesn't matter with replacement. So let's start here. So here's a tree that might help you think about this in the case of rolling a fair die. So imagine that this represents you sort of rolling, and you could roll a 1, a 2, 3, 4, 5, or 6. So you have 6 possible outcomes the first time, and you don't use up any outcome. So you could roll, for instance, a 6 and then roll a 6 again. So every time you roll, you've got 6 options, and that doesn't affect your number of options the next time. So each time you could choose, let's call the number of outcomes n, and then you're going to iterate the experiment k times. So what that means is that the number of options is n to the k. And I noted that here. So k is the number of things we choose, and then n is the number of things we choose from. So for instance, how many total outcomes are there from rolling a fair die twice? Well, the answer is 36. And hopefully that's pretty intuitive. You can either use the formula, so 6 squared is 36, or you can kind of just think, well, I've got 6 outcomes here. I've got 6 outcomes for each one of those things, so I should multiply the 6 outcomes here by the 6 that each have and get 36. So let's think about a slightly different situation. Suppose that we are tasked with finding all the unique orderings of the letters in the word badger. How would you go about calculating this? So once again, you want to start by thinking about how many options you have for the first place, which is 6. But what's different here? Well, if we're rearranging the letters and we are not allowed to repeat them, which is sort of implicit in the word rearrange, we lose 1 option each time. So suppose we start with G. Then we only have 5 options for the next letter. We have B, A, D, E, R. And then once we pick that, let's say we pick D, then we have 4 options, B, A, E, R, etc. So we can actually now put that factorial to use. If we think about, okay, we're losing 1 option each time, but I should still kind of apply that same logic from the last slide. So we want to multiply the number of options we have at each step. Well, that's kind of nice. We had 6 options to start, then 5, then 4, then 3, then 2, then 1. And that happens to just be 6 factorial. So that's the answer to this question. What if I ask a slightly harder question? What are the possible ways of arranging 2 of the 6 letters in Badger in a unique sequence? We're going to use the same logic as before, and you can do this by hand. You can just say I have 6 options the first time, then I have 5, and then we're done. You can check this on your own. It's not impossible to do by hand. But I want to ask you, how can we write this more concisely, right? Because the answer here, 6 by 5, is a little bit problem specific. So think about our task here. We want to take n factorial, but only go through the first k steps of n factorial. So what we should do is divide by n minus k factorial. Here that gives 6 factorial over 4 factorial. And note that that's going to mean, if you think about it, we're going to cancel the 4s, the 3s, the 2s, and implicitly the 1s, although we don't need to write them. And that just leaves 6 by 5. And that's the answer that we got before just through intuition. So that gives us a formula for permutations when we can't have repeats. So let's summarize what we just did. We first thought about how many ways we can arrange n items when we can't reuse any, and we used them all. That was just n factorial. Then we did the same thing, but we declared that we only wanted to pick k items. So that turned out to be n factorial over n minus k factorial. You can actually think about that first scenario as really just a special case of the second. In that situation, n is equal to k. We're picking all of the items. So this might seem problematic because we'll get a 0 in the denominator, but actually 0 factorial is defined to be 1. It's interesting, we don't have space to go into it here. There is a bit of an intuition for it, which is that if you think about factorial operators as kind of giving implicitly numbers of ways of arranging things, that's really the main use that they have, then you can think about the way to arrange 0 things as 1 in a sense, like what's the only way that something could not exist? There's just one way for it to not exist. That's a loose intuition, but it might be helpful. So anyways, if you pick all n items, you have n factorial over n minus n factorial, which is 0 factorial. That's n factorial over 1, or n factorial. So we actually saw that our first example was just a special case of the second. The general formula for the number of unique orderings of k items from a set of n is n factorial over n minus k factorial. It's a good thing to know. So what about if we have a combination where order does not matter and implicitly we have no repeats? So let's take our same example that we've been working with, except now we want to think about how many unique groups there are of any two letters from the word badger. It's pretty easy to count by hand, but let's think about writing it for a more general case. So let's consider this. We already have the number of unique orderings that are possible for two letters. So for example, starting with B, we have BA, BD, BG, BE, BR. And you can just kind of quickly mentally count that by seeing, okay, here, 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 here. And incidentally, you can also note that this gives us a sense for why it is the case that we have 6 by 5 in the way that we figure out all of the unique permutations. It's that we have 5 options here once we select a first option, and then we have 6 options. So we should try to add up 5 6 times or multiply 6 by 5. Okay, but let's come back to the problem of combinations or unique groups, not unique orderings. So later, we'll get each of those again. So for instance, when we start with A, we'll get AB. So we would go AB, AD, AG, AE, AR, and we count AB again, but that's the same group as BA, just a different order. And then when we do D, we would go DB, DA, and okay, we get DB, that's the same group as BD, just with a different order. So our old formula overcounts, and it actually overcounts each group by the number of unique orderings of that group. So for instance, here we can kind of sense a pattern. When we have a group of size 2, that means that there's 2 ways to order it, BA and AB, for example, DB and BD. So we want to actually just use our old formula, but now undercount. So it's simple. How many ways can you arrange k items? We found before that the number of ways you can arrange all of the items in a set is just the size of the set factorial. So how many ways can you arrange k items? It's k factorial. Then you divide by that factor. So this gives the very famous formula for combinations, or in other words, the number of ways you can form unique groups of size k out of a set of size n, where you can't repeat things. So you can't, for instance, you couldn't use B twice in our example, and you don't care about order, which is implicit in the word group. So this quantity is so important that we have special notation for it, and we refer to it as the binomial coefficient. And this is where the binomial distribution comes in. The reason is in the appendix. I also have a YouTube video on this that shows you how to prove the power rule in calculus. So this is often written as n choose k, that's how we pronounce that, or like this. And the second notation here doesn't have any special meaning associated with this verticality. It's not a division or a vector, it's just notational. So this also means n choose k. And this tells us to basically plug n and k into this formula here. And what that gives us is the number of unique groups that we can form out of a set of size n, given that we want a subset of size k, or groups of size k. Here you can visualize this. You might be interested to see the pattern here. The coefficients are the entries in Pascal's triangle. Remember that you can actually form Pascal's triangle even if you only know basic arithmetic. So imagine a row of zeros here and here. Then the way you get the, just a 1 here. The way that you get any entry in the triangle is you add the stuff that's basically to the left of an entry and to the right of an entry. So 0 and 1 is 1, 1 and 0 is 1. Then here we would say, okay, 1 and 1 is 2, 1 and 0 is 1, 1 and 0 is 1, 1 and 2 is 3, 2 and 1 is 3, and then the edges are always 1. 1 and 3 is 4, 3 and 3 is 6, 4 and 6 is 10, 4 and 1 is 5. I'm just picking some randomly. 56 and 70 is 126, 126 and 84 is 210, etc. So you can form this triangle, and you may have done this in an early math class. But note that these are also actually the binomial coefficients. So for instance, if we're trying to think about, okay, I have a set of size, let's say 4, and I want to run through the number of ways to pick sets of size basically 0, 1, 2, 3, and 4. Okay, well, that's 0 through 4, that's 5 numbers, and the binomial coefficients are 1, 4, 6, 4, and 1. In other words, there is one way to pick none of the items in a set of size 4 intuitively, right? You can't do that, except one way, don't pick any of them. Then there are 4 ways to pick an item of size 1 from a set of size 4. Okay, that makes a lot of sense, right? You could pick any of the 4. Then there's 6 ways to pick a group of size 2 of that set of 4 items. Then there's only 4 ways to pick a set of size 3 from that set of size 4. And that should also make sense because notice that this is symmetric, by the way. But that makes a lot of sense, right? Because when you select a set of size 1 or a set of size n minus 1, then implicitly there's really only one way to make each of those things, right? You can just you decide which thing you're picking or which thing you're not picking, but each time you're either picking one thing or not picking one thing, and intuitively those should be the same. We'll come back to that later on. This part isn't super important, but I just thought it might be useful. Incidentally, the reason that this holds true is that it has to do with the fact that if you turn these basically all into kind of binary and think about almost like a frog hopping down a lily pad, like how many ways can the frog hop to a particular lily pad, it actually makes a lot of sense. So we need to establish one final probability rule before we put this all to use. Note that in general, the probability of B intersection A, or the probability of A and B, is equal to the probability of A times the probability of B given A, or the probability of B times the probability of A given B. Fortunately, this is pretty intuitive, but it's also trivial when the events are independent and A supplies no additional information about B, meaning that the probability of B given A is just the probability of B. So if A and B are independent, the probability of B and A just reduces to the probability of A times B, the probability of B, I should say, or the reverse. So an important point is that independent is not the same thing as disjoint. So if we come over here, note that when events are independent, they actually can have an intersection, and in fact, they really need to. And note here that these two appear to be independent, but R and T appear to be not independent or dependent. Why is that the case? Well, think about the probability of, let's say, T. So the probability of T overall is about 1 in 6, but the probability of T given R is clearly almost 1, right? It's very large, so that means the events intuitively are not independent, and the same is true in reverse as well. So the probability of T given R, R given T, the probability of R overall is quite small. It doesn't get much bigger when you account for T, it gets bigger. It's still improbable, but it's a question of like 1 in 30 versus 1 in 3, something like that. So still improbable by the conventional meaning of less than 50% chance, but much more, relatively speaking, probable. So that's a way to visualize dependence and independence. So these two events are clearly dependent, and you can see the footnotes for a brief little proof of why using areas, why it is the case that both of these ways of writing this are equivalent. Note that J and K do appear to be independent, because if you think about it like this, the probability of K and J over, say, the probability of K, it's equal to the probability of J given K by definition. So that means that is the conditional probability rule there. But if we think about it, so this area here, P of K and J over the P of K, appears to be about 1 in 6, somewhere in there. That's probably maybe closer to 1 in 7, but I wrote 1 in 6 here. But then if we think about that, so that's equal to the probability of J given K by definition, right? But then we see that the probability of J itself appears to be about 1/6 of the sample space. So if we think about, again, calculating the probability of J given K, it's this overlap here over the probability of K, which appears to be about 1 in 6, but the probability of J itself just appears to also be about 1 in 6. Sorry, this click pad is extremely sensitive. So that means that intuitively, knowing K doesn't actually change our overall estimate of j that much. The ratio of the intersection to k is roughly equal to the ratio of j to the entire sample space. And so what that means is that this doesn't really give us a lot more information, and j and k are independent. Fortunately, though, again, the point is that when they are independent, as they very often will be in our class, then the probability of two things happening is just equal to the probability of each of them happening individually. So let's connect this to the distribution of many samples. So the probability of independent events is just their product. So the probability of any sequence of, say, a sample of 5 coin flips with 2 successes generally looks like this because the events are independent. So the probability of H, H, T, T, T is the probability of H times the probability of H times the probability of T, or you can just write this as Q of T, where Q is a complement of P. I'm actually going to change that because I don't want that to confuse people, and we can also eliminate this as well. Yeah. I don't need to include this information. So, generally speaking, the probability of any sequence of k successes is equal to p to the k times 1 minus p to the n minus k. And stop and meditate on that for a second because that's a little bit tricky. Note that we're going to have the probability of, k successes by definition. So we multiply p by itself k times. That's what p to the k means. And then we immediately know the probability of the other alternative because this is a binary outcome. So the probability of the alternative is 1 minus p, or q if you must. And then that is taken to n minus k because we have n, basically the set is size n overall. And once we select k, we have n minus k things left over. So pretty straightforward. But there's one final complication, and this is what leads us to the definition of the distribution. We're actually more interested in the probability not of some specific sequence of successes and failures on a dummy. This is actually uninteresting in the context of a sociological sample. It's not even really well defined. So for instance, we don't really care about the order in which people enter the sample. And so if we think about whether or not someone is married, we don't really care if we have, 5 married people in a row, then 4 unmarried people, or whether they go one, the other, one, the other, one, the other. It doesn't make a difference to us from the standpoint of any question that we're going to ask in sociology. What we actually care about is the probability of observing k successes in a sample of size n, whatever order they come in. And again, in this case, order isn't even really well defined because we have a sample that might be, say, collected over time. There's people that enter the sample, but they don't finish it. It really doesn't make that much sense to say that we care in this case about order, the order of the items in the sample. So here's our general task. The probability of any sequence of k successes is p to the k times 1 minus p to the n minus k. But we're interested here only in the probability of k successes, not a specific sequence. So how do we add up the repeats? For example, if I flip my coin 5 times, I might want to know how probable getting 3 heads is. The sequence HHHTT is just as valid here as HHTHT. Both of these would involve getting 3 heads. So note that we can think about this. So intuitively, if I flip a coin 5 times and it's got a 50% chance of landing heads, that means that getting 3 heads should be one of the more probable outcomes. There's not that many distinct outcomes. You can only get 0, 1, 2, 3, 4, or 5 outcomes, so there's only 6. So that means that it's probably not the case that there's only a 3% chance of getting those 3 heads. Because note also that also is immediately the probability of getting 3 tails because they're each equally probable. So together, when you flip a coin 5 times, 2 of the 6 outcomes that seem intuitively the most probable are only about 6.25% of the outcomes. That doesn't make any sense. Well, here's the problem. We're undercounting, right? So we're only counting in this case implicitly when we do p to the k times 1 minus p to the n minus k, we're implicitly multiplying out the probability of a heads, 0.5 times itself 3 times, multiplied by the probability of a tails to the n minus k, which is 0.5 times itself 2 times in this case. So how can we add up all those things? Well, what we would want to do in this case is think about how many ways can we select 3 out of the 5 trials to have this outcome. So how many ways can we make 3 out of the 5 trials successes? And so 5 choose 3, you can calculate that in a couple of different ways. I'll just show that Google will calculate it for you if you like. So let's try that here. and you can see that it's 10, but we can also enter it into our formula. So the way that we would do that is we would say, okay, well, we've got 5 factorial on the top, and then in the denominator, we've got 5 minus 3 factorial, and then we divide that by what's, in this case, our number of items, 3 factorial, right? So we have 5 factorial over, and then we've got in the denominator, 5 minus 3 is 2 factorial times 3 factorial. So probably the simpler thing to do is take the 3 factorial out of the 5 factorial. So we have 5 times 4, and then divided by 2 factorial, which is just 2. So we have 5 times 4 divided by 2, or 10, right? So we get 5 choose 3 in that way. You can also write this out by hand. You don't have to do it just in your head like that. You can also use Google. This part, like knowing where the formula comes from, is quite useful, but in practice, you don't need to calculate it by hand that much. So in this case, then, we just multiply our answer by 10, because this component here is 10, and this actually is going to happen to be the same thing as before. Oh, by the way, this should also be... This is a little easy to miss, because when you have 0.5, right, for the probability of a success, that means 0.5 is the probability of a failure. And actually, no matter how you kind of sparse these out here, so 0.5 to the 3 times 0.5 to the 2 is the same as 0.5 to the 5, which is the same as 0.5 to the 4 times 0.5 to the 1. So it's easy to catch, or miss, sorry, little mistakes there, because the math will work out just by coincidence. Okay, so this is what we do here. And you can also kind of think about this. So we saw that there are 32 possible outcomes in this case, right? So you've got 2 outcomes each time, and that's using our rule from before, n to the k, since we can repeat events here. You can get a heads multiple times, so there's 32 possible outcomes. And then we can actually count out by hand all the sequences. So we've got triple heads, 2 tails, then we kind of shift the tails over, so double heads, tails, heads, tails. Then we can kind of shift this next tails over, so heads, heads, tails, tails, heads. Then we can, again, kind of shift the tails down, so heads, tails, heads, heads, tails, moving this back out. And then we can do heads, tails, heads, tails, heads. And then finally heads, tails, tails, heads. And then we're now coming to the situation where we start with the tails, so we have tails, tails, heads, 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 tails, heads, tails, heads, heads. So we kind of shift the t over, shift the t over again, tails, heads, heads, tails, heads, and then shift the t to the end, tails, triple heads, tails. And if we count these up, this here is obviously 4 with a couple doubled, and then with a couple extras, so that's 10. 10 over 32 happens to be 0.3125, which is the answer that we got. So this is all pretty intuitive. Let's visualize the probability mass function from that last slide really quickly. So here I generate y values for a given value of k by finding all possible sequences for that value and then adding up the probabilities. In other words, I just used the binomial distribution formula here. So you can see that we got for k in this case, sorry, I don't know what that is. We got for k in this case for 3, 0.3125, but we also would get the same thing for 2, which again should be intuitive, because this also means getting 3 tails and 2 heads. And since tails and heads are equally probable, this should be the same thing. And you'll see indeed that this distribution is often symmetric, although not far from always, but it often ends up looking fairly symmetric anyways in large ranges. Okay, cool. So we can finally write out our probability mass function for observing k successes out of n trials for a sample of size n, given some population probability p, and it is this. So we say the probability that a random sample x, or the number of successes in a random sample, I should say, x, is equal to some actual number of successes k is given by n choose k times p to the k times 1 minus p to the n minus k. And we derived each part of that before. And here it is written out in English. You can see the binomial distribution in action here. So this is a situation where I, again, kind of use the idea of events that are equally probable. So this represents flipping a coin. And I actually went ahead and simulated here what it would look like to take very many trials. So this is really interesting because it shows you the power of a sample size. So when I iterate this a million times, but I only have a sample size of 1 here. So I flip a coin once, I consider that a finished experiment. I flip a coin again, I consider that a finished experiment. Then I plot all the results. The resulting sampling distribution, if you like, actually just looks exactly like the probability mass function for a single outcome. And that's because a binomial sample of size n equal to 1 is actually just a draw from a Bernoulli or a dummy variable. It's a realization of one of those variables. So this doesn't look any different to the probability mass function for, say, a coin, which we've seen before. But note that as you increase the sample size, so that means for each experiment, I'm going to run, say, 5 trials. In other words, flip the coin 5 times. Or I'm going to run an experiment where I flip the coin, say, 100 times. And those trials are all the entire thing. And then I iterate that a million times, or iterate that a million times. Or maybe I even flip it 500 times and then iterate that a million times. So this here represents ultimately 500 million simulated trials. Note that it starts looking, well, it looks very normal, right? Which is a very cool fact. Just as a reminder, again, big bold P is the probability of K successes. It's what's known as a binomial probability. Little italic P is the probability of a single success. It's the mean of the dummy variable in the population. So there's a key caveat here, and this comes up very often, so don't worry if this is tricky at first. The simulation to the right and the simulation that we'll do today in class represent the taking of many samples. In practice, we only take one sample. It's just enough to know that it's drawn from one of these distributions. We don't actually have to simulate it. So for instance, if you have a sample in our class, let's say everyone's here and we have a sample of about size 70, we're not going to consider that a sample of size 1 with 70 replications. If you actually have 70 observations, you should pile it into a sample of size 70 and know that it's taken from a distribution that would be between these two here. So it would be taken from a distribution that I didn't plot of n equal to 70. You don't actually have to do all the other iterations. You can just know that it's drawn from that distribution, right? So the n's to the right are the sizes of the individual samples, which you actually can't directly see on the graphs. It's not visible. So again, this is different than the number of samples taken or replicated or simulated. In this case, it is 1 million, and it's represented, although again, it's kind of hard to see, but in theory, in this case, since these are bar graphs, that means that the heights of all these things have to add to 1 million, basically, or 1 million divided by the total. So they have to add to 100%, basically. So this number of replications is arbitrary. I just picked a large one so the patterns are clear. In practice, you don't need to do these simulations. You just need to gather a large enough sample so that you can say, oh, my sample was taken from a distribution like this, or it was even taken from a distribution like this, or ideally this. And note that 500 is actually larger, or smaller, than a lot of the sample sizes we've seen, for instance, in the GSS. One last clarification, and I noted this before. Note that a sample of size n equal to 1 is a binomial sample, but it's just a Bernoulli or a dummy variable. So taking a huge number of samples, but only doing one person each time and recording the result each time gives a shape for the probability mass function that just looks like the population PMF for that variable. So that's not very powerful. If you have a bunch of observations on a dummy, consider them taken from a sample of however many you have, and then that means that they're drawn from one of these distributions. That might sound weird because it's like how are you changing that? You just conceptually, change what you're doing conceptually. But that's sort of the point, is you want to actually more powerfully conceptualize this as being taken from one of these distributions here. And when you have these bigger samples, the probability mass function of possible counts k starts looking more normal. So here are some key facts about the binomial distribution. Intuitively, the mean is n times p. There's a detailed proof in the back, but the intuition is we're adding up n dummies, and they each have an expected value of p, so they should probably just have a mean of np, right? So in other words, the expected value of the binomial distribution, we're adding up a bunch of people that have zeros or ones in this variable. In theory, the mean should just be n times the probability, since that's the number of people you expect to be ones. The variance is n times p times 1 minus p. Again, think about it like this. We already know that the variance of a dummy variable at the population is p times 1 minus p, and the total variance in that case is just the sum of the variances. By the way, note here that we're not messing around with any n minus 1 stuff, because these binomial distributions are not observed distributions. They are theoretical distributions. So this is not the distribution in a particular example. It's a distribution of many samples. That's a sampling distribution. It's a good approximation to the normal if np is greater than 10 and n times 1 minus p is greater than 10. Otherwise, it gets a little tricky because you have a situation where one of the n's is going to be truncated. Because the number of successes k must be a non-negative integer, that means that if you get close to 0, then you have... the point basically is that the distribution is going to be truncated at 0 no matter what. But if NP is far away from that end of the distribution, then you have a truncation in a realm or a neighborhood of the graph where the probability was extremely low anyways. But if you don't have that situation, so like let's say you have a very large n, but your p is very small, so n is say 1,000, but p is say, or let's say to make the math easier, let's say n is equal to 100, but p is equal to 0.005, then you're in some trouble because the center of the distribution is going to be located very near to zero, which makes it not a good normal approximation. The tomato problem in the book is a good example of that, by the way. I know I'm just saying that stuff out loud, but hopefully you can visualize it. Finally, the sample size population caveat. So this approximation is best if the relationship of the population size to the sample is pretty large. So the population should be much larger than the sample. The reason for that is basically the following. It's the hypergeometric caveat. Technically, we change little p very marginally when we sample without replacement. So in other words, the probability for each individual is not stable because it changes very, very minutely. So for instance, if you say you're taking a sample of 1,000 voters, the probability of the 1,000th person in our sample having been a voter changes only minimally after we include the first 999 people. But by the end of the sample, the 1,000th person has a slightly different probability than did the first person who was taken from, a population where we hadn't yet disturbed it, right? And in most actual samples, you can't end up in the sample twice. But fortunately, this actual difference is extremely minimal because the US adult population is orders of magnitude bigger. So when we take someone out of the population and put them into the sample, we're not really changing the population very much. Finally, this is where we would come to the point where we would do a simulation in our class. And I'm going to pause the lecture here since I now have to go teach that class. Bye for now. So in my class where I taught this, we did a simulation of the binomial distribution. I had people pull out a coin, flip it 25 times, and record just the number of heads. So you want to think carefully about what's happening here. So each flip of the coin is a trial, and each person's 25 flips are a sample or an experiment. So this is a rare case where we actually are doing many different samples. And a common question that I get from bright students who are thinking about this stuff critically for the first time is, if I have a big sample, do I consider that multiple samples or do I consider it just one large sample? What's better from the standpoint of the binomial distribution? And what's better, a number of different people had opinions on this. Isaac Newton wrote to Samuel Pepys, the great English diarist, and commented a little bit on this in the context of gambling, but it's similar in probability and statistics. Basically, the best choice here is going to be to just take the large sample size. So in practice, if you ever had this number of trials, I think we had something like about 100 people do this, a little bit less, and like total across semesters. And then we had 25 flips each, so of course that's 2,500. You would be best off considering this as sample of size 2,500 rather than 100 samples of 25 because you really can't do much besides just treat each of them individually. So that's kind of the point, is that our sampling distribution knowledge applies to one sample and it tells us what sampling distribution that sample comes from. It doesn't really matter if you have many different samples. I mean, there is merit to doing an experiment multiple times. It's called replication in the scientific context, and it's important to do. But the best thing a single researcher can do is combine his or her samples. Pardon me, sorry, I'm getting over a bit of a cold here. So that's the basic idea. Onwards, let's look at this. So I have people enter this into a form, and then this is a Google form. By the way, if you're watching this in the future, feel free to maybe enter this if you do the experiment. It's kind of fun. And then let's look at the results. So this is what it looks like when you simulate a sampling distribution. And basically what's happening here, what all of these things on the x-axis represent are different possible numbers of successes of flipping a coin 25 times and the successes being heads. So very understandably, the mean of the distribution appears to be between 12 and 13. The mode is 12, but 13 is behind. It's a close second here. And actually the expected value of this distribution is 25. So that means that as we did more and more replications here, we should eventually see that this thing will start to look more or less exactly binomial. And you can actually pull this code if you want and run this yourself. So the Stata code's a little bit fancy, not to toot my own horn too much, but you can just pop this into a do file and run it, and it'll actually pull from this website. We had a little snafu in class because a couple people in class wrote down letters in the string, so you need to, or wrote down, sorry, letters in the variable, so you'll need to destring the variable. There's some other fancy bits here, but basically this is how you reproduce this. And you can actually see in a variety of different ways what this in theory should look like. I could show you in Stata, but I want to show you in a way that's accessible. So let's actually look down here. Show you in a way that doesn't require you to be too comfortable programming. So this is a simulation from David Lane. This is a really cool website. And so we would do here, we're going to write down our n. So our sample size here is, it's not the number of replications, by the way, because this is going to show us the true distribution of this distribution here. So this is a sampling distribution. The binomial distribution is a sampling distribution. And this is going to show us the true sampling distribution here. So we don't need to do any replication. So what we're doing here is we're going to write down 25. And then we're going to say our pi. Remember that pi sometimes means probability in this context. So our pi doesn't need to change, it's 0.5. And we actually don't need to do anything here. You can see that this basically looks just exactly like the distribution we had, more or less. Pardon me. You can see, and I changed probabilities to basically to 100% here, or percentages, not decimals, but we would get basically the same thing. And you can see it's centered on 12 and 13, etc. So that's what this would start looking like eventually. So I wanted to now show an example of how we can put the binomial distribution to use. So there's kind of two uses here. One use would be a situation where you know the true population probability, little p, and then you're interested in the probability of observing a certain sample. That's the situation that we're going to look at first. It's less common in reality, especially in social science, but I want to start with it because it's simple. So we've kind of already been doing that with the coins, or in many different ways. That's kind of the logic of what we've been doing with the coins. But I now do want to go ahead and just kind of show an exact example. So think about this possible setup. The second generation of a certain cross of sweet peas has probability 3 and 4 of having red blossoms and 1 and 4 of having white blossoms, and the blossom colors of separate plants are independent. So what's the probability that exactly 3 out of 4 of these plants have red blossoms? So what we want to do is first just write down the formula for the binomial distribution. I don't want to encourage too much, plug and chug type behavior, but that said, now that we've learned the binomial distribution and learned where it comes from, we can kind of treat it as an established fact. So we write down our formula. It's, remember, big P of x equal to k. So what that means is the binomial probability, or the kind of probability of a sample having x successes equal to k. So x is just a random variable denoting the number of successes. K is the actual number of successes. So for some actual value of x, k, the formula is given by n choose k times p to the k times 1 minus p to the n minus k. And again, just to review, where does all that come from? If you think about it, the idea is that we have, some particular sequence that we're going to calculate the probability of. So for instance, if we had, like in this situation, we've got 3 out of 4 plants having red blossoms, we could calculate the probability that the first 3 plants have red blossoms. That would be 0.75 times 0.75 times 0.75, or p, which is 0.75 here, to the k, which is 3. And then we would have 1 minus p, or 0.25 to the n minus k, which would here just be 1. Now, the problem with that is that there's other ways to get 3 out of 4 plants having red blossoms. For instance, we could have 1 plant have red blossoms, 1 have white, and then 2 more have red. And that would be represented by 0.75 to the 1 times 0.25 to the 1 times 0.75 to the 2. And of course, you could rearrange it, and you would see that that's the same exact thing that we got before. by the commutativity of multiplication, but we didn't count it twice before. So it's kind of helpful to write it two different ways and say, oh, well, there's two ways this could occur. So it turns out to be the case that there's a handy way to count the number of ways to choose k things to be successes out of n, which is n choose k, the combination formula. And recall that that's n factorial over n minus k factorial times k factorial. So those second two things are both in the denominator. Pardon me, still very sick. And then what we want to do is just go ahead and plug and chug, but it's important to see where all of that comes from, right? So we basically, what we do, we find the probability of some particular sequence of having exactly 3 red blossoms and 1 white blossom. It doesn't matter what we conceive of that as representing. It's typically written in this way to indicate that the simplest way to do it is say, okay, imagine that the k successes all come in a row and the n minus k failures all come in a row. Of course, that and really any particular sequence are all equally improbable. They have low individual probability. But then the point is that we want to figure out, okay, but we could actually choose many different ways to have k successes in at least most cases. Not always, but oftentimes there's many different ways for that to happen. Either way, whether there's many or few, n choose k will count them correctly. So first, let's see what this looks like when we treat this as an actual function, because remember that this is a probability mass function. So let's write this as a function of k. So the distribution will look like this, and now you can see that this has the form of a function, right? There's only one variable, so we can plot this with k on the x-axis and big P x equal to k on the y-axis. And let's go ahead and do that now and see what it looks like. So it looks like this, and you can see that hopefully this feels fairly intuitive. The highest probability of event individually, of course, is getting exactly 3, but 4 and 2 also are in there, and then 0 predictably is kind of at the bottom. Let's again kind of check and see what that looks like with the calculator here. So in this case, we have a sample size of 4, probability of 0.75, and let's just say we're interested in exactly 3. So let's say that our work by hand actually matches what we would get here on the graph. So probably the best way to do this, there's a variety of different ways. If you really did want to do it by hand once, I think this is the way to do it, is go to Wolfram Alpha, which is kind of an AI calculator. And the nice thing about this is that we can actually test that our hand calculations work, but we don't have to think about finding the kind of crazy complicated math input here. We could do that, but Wolfram is smart enough that it'll actually do a good job of interpreting what we mean in natural language. So we want to find 4 choose 3, which happens to be 4. And I've mentioned before in class that anytime you have n choose n minus 1, it's always going to be n for reasons that you can work out. It's pretty intuitive. But let's still do this by hand. So we want to then multiply that by 0.75 to the 3 times, we can just write 0.25 since it's to the 1. And oh, we want to, make this clearer. Let's put this in brackets. Yeah, there we go. And you can see that Wolfram even nicely prints out what it's interpreting it as in mathematical notation here. So this is really cool. So then we get this answer here, 0.42, etc. And that's the answer that we got using the thing here, using basically Stata. I wouldn't recommend doing it this way, again, because it's difficult to do in Stata. Here's another way to do it. This way basically gives you an exact binomial answer. Oh, we already did this already, sorry. This way gives you an exact binomial answer. There's a whole bunch of ways to check this, right? You could do it purely by hand. You could use a calculator, which I think is not a bad idea. You could, for instance, just do the normal approximation, and in that case, the online statbook normal approximation will work well. Pardon me. So that's one way to think about this type of problem, or one way to think about the binomial distribution and its uses. But there's another use of the binomial distribution, which is the following. Oh, and then here I showed how to do this by hand. So suppose that we had 60 plants and we're actually unsure of the value of P. So maybe we suspect improper crossbreeding or some kind of problems with how we bred the plants, whatever. So we want to test the value of P, and let's just assume that we have P naught here equal to 0.75. The 0 subscript, which is pronounced not in this context, so we'll later discuss H naught, a null hypothesis. This is just a value of a null hypothesis P. basically represents our guess, right? And we can pick anything we want. You don't have to, there's no constraints on what you would guess here. It should just be a phenomenon of interest or a quantity of interest. So now let's find the probability of a sample with 40 successes or fewer in a sample of size 60. So this is what this looks like. Note here that these heights have to sum to 1 because this is a probability mass function. And this is, by the way, the entirety of the thing, right? So you can't have fewer than 0 or more than 60 successes here. And you can see that the kind of cumulative probability of this number of successes, so 40 or fewer. And the reason why 40 or fewer, by the way, is that when we come to continuous distributions, the probability of any particular outcome, of course, has to be 0 because of that gotcha that is very frustrating at first. But remember that the probability on a continuous distribution, so one described by a normal curve, for instance, the probability of any actual observation is 0. So we want to think about ranges. Here it makes sense to think about this as 40 or fewer because it gives us a sense of like how weird are these results. So basically, how often would you see results this weird or weirder, as we'll often say, if the null were true? So this is the distribution under the null hypothesis. This is what the distribution looks like if p is equal to 0.75, and we can calculate it here, right? So now k is a variable and p is fixed, except in this case, p is something that we're guessing and k is something that we observe. So it's kind of funny, right? Because before we were trying to figure out, given a known true p, what are the probabilities of different samples? Here we're doing the same thing, except we're actually inverting what we know. We know the number of successes, we don't know p, but we're posing a counterfactual question and saying, what would it look like if we had this true p, little p, by the way, and then we had this number of sample successes. And so here, if we actually calculate this out, this is tedious to do by hand because we have to sum it up. So we can let Stata do it if we like. Note that because we want a cumulative probability here, Stata's cumulative binomial function will help us out. And we just put in here n, k, and then p. And you can get an exact value that way. But we can also use basically the online stat book as well. So let's go ahead and see what that looks like. This happens to be about 0.09 or 9%. Is that improbable under the null hypothesis? By a colloquial definition, yes, but how do we really decide on a cutoff there? It turns out that there's really not a good answer to that question, and this is a source of great consternation and debate in statistics. A common cutoff, and cutoffs are generically termed alpha, which is one of many meanings of alpha in statistics, is 0.05. But that also depends on whether we were looking in just this tail or this tail as well. So maybe we would be interested to know. For instance, you can calculate the expected value of this distribution, by the way. It's 0.75 times 60, so hopefully you can see that it's 45. And then you might say, okay, well, 40 is 5 away from 45, so what if we also looked at 50? And, you know, we could actually show what that would look like in the calculator here. So I'll show you how to use the calculator. So 60.75. We could say, we'll have to do this by hand, but we'll do here above, let's see, that would be 49, so 0.08, and then below, here would be below 41, it's 0.09. So it'd be about 17% chance of results like truly this weird or weirder in the sense of this far above or below the expected value. So there's a variety of different ways of doing that. We'll get to that later. Those details are pretty annoying, to be honest, and not the fun part of statistics, but they are something that you have to deal with as a practitioner. So that's where I'm going to leave this. The TAs will cover this normal approximation in class. Pardon me. So I'll let them handle that, and I'll see you all next time.